Thank you everyone for coming here today. I want to acknowledge the traditional owners of the land on which we're working and learning, the Wurundjeri and Bunurong people of the Kulin Nation, and I want to pay my respects to elders past, present and emerging and anyone here today. So I want to quickly introduce Neil and then I'll let you get started. Neil said he's got a lot of slides, which is code for if it hits 12 p.m. and you must leave for a meeting, you can sort of vacate the premises in a respectable, orderly fashion.
Absolutely.
Yeah. Okay. So Neil is on sabbatical, visiting us from the University of Edinburgh. So we've gifted him collaborations and fine weather, and is going to be talking to us about information seeking and how it might deviate from some kind of normative principles, which I feel like all members of the Hub are on board with. So yeah, cool. Thank you.
Brilliant. Thanks very much. Thanks for having me. So yeah, this is an attempt to sort of connect together various older and newer projects under a kind of semi-coherent theme. We'll see how well that works. Starts with this sort of the observation that if you're trying to study the mind, it's important to remember that cognition is loopy. By which I mean, one aspect of studying the mind is studying how we learn, how we update our beliefs from observations. Another aspect is studying how we use our beliefs to guide our actions, to gather rewards and achieve our goals, perhaps decision making. But of course, every time you take an action in the world, that changes what you see next. So in fact, there's a circle here, and an important aspect of action selection is consideration of what it might tell you, which might in turn change your beliefs, which can change and empower you to better seek your goals in future. And I don't think this is a sort of side aspect of cognition. I think information seeking is pretty core from the ground up. We're born into a world where we spend a lot of our time as embodied agents, interacting with the things around us, poking and prodding them. We're constantly having to direct our attention, given the sort of barrage of stuff that's happening around us. We need to be very careful about what we even look at. And of course, as adults, and as we think more about higher level cognition, a lot of what we do is really information seeking with respect to our current task, asking questions of one another and of the internet. And, as scientists, we try to distill the principles and norms of information gain into kind of formal procedures so that we can do it well. So this talk's all about information seeking. And as a cognitive scientist, I like to come at everything from a rational analysis perspective. Unfortunately, I'm not the first to do so here, so this is a problem that people have thought about quite a bit. And the normative idea here is that when it comes to performing actions, looking at data, asking questions, or running experiments, you should be trying to do these to maximize the expected information that you can juice out of the situation through that choice. And this is sort of a proxy for empowering yourself to be able to make better decisions in future by reducing your uncertainty about the dynamics of the environment that you're working in. And there's a sort of computational story about how to do that. It starts by laying out all your hypotheses about what could be true of the world, and laying out the space of actions that you could perform in this current context, whether those are questions or actual experiments or queries or choices of where to look. And then there's the consideration of all the things that might happen if you were to perform those actions. And when you sort of mix all of these dimensions together, you can kind of do what's called a pre-posterior analysis. So you can imagine, what if I were to take action M in situation X and see data Y? How would that affect my hypothesis, my probability distribution over the hypothesis space? And how likely is that to actually happen given my prior probability distribution of the hypothesis space? So for every possible future, you can evaluate how much better or worse that might be than where you are right now. And then you can calculate a great big fat expectation over all of these things. So what's the expected reduction in uncertainty or increase in information that you can expect with respect to your global hypothesis space, taking this action under consideration of all the things that could happen if you did take that action. It's a computationally costly norm, so it sort of generally depends on the product of the hypothesis space size times the action space size times the sort of hypothetical data space size to the power of the horizon, that how far into the future you try to think. But at least it's sort of well posed-ish. and it has been used quite extensively as our sort of descriptive and prescriptive norm for thinking about these questions. So perhaps quite famously, this was sort of brought into the cognitive science consciousness by Oxford and Chater in their paper, which reanalyzed the Wason card selection task. This is a task where people are trying to, confirm a rule by turning over cards. And prior analysis had kind of said that people are hopeless at this because the things they did are illogical. They don't capture the sort of syllogistic nature of this scenario. But Oxford and Chater argued that if you put a prior over the possible contents of the deck of cards and the likelihood of different rules, then suddenly what people are doing starts to look quite information efficient and sort of grounded in real-world rule selection problems. At the low level, you see these kinds of analyses of sort of our eyes saccade around a scene in a way that's actually very information efficient in terms of telling you what's in front of you. But there's been a sort of tradition of looking at information-seeking types of games with children and adults to see and arguing that the things that people are doing to test hypotheses in these games is efficient. So looking at how kids play the game Guess Who, where you try and figure out who's on the cards that the other person has, or Battleship, you're trying to figure out where the opponent's ships are. You can use this kind of norm to analyze these kinds of things. Also how people interact with a causal system, as we'll see in a second, with the goal of trying to figure out what's causing what within it. And prescriptively, many have argued that when you design your next experiment, you should be trying to maximize this quantity. You should be picking your design variables to maximize how much information you can get with respect to your theory hypothesis space. Various sort of perspective books have sort of taken this as the organizing framework for the study of information seeking, active learning, and the drive for knowledge. So I'm going to start with a sort of relatively constrained version of this, an experiment that I ran a few years ago where this kind of works reasonably well, and then we're going to depart from that. Todd Gurekis, Ruggieri, and I had some fun building this box back in Berkeley when I was a research assistant. It's a sort of a magic toy box with a mysterious causal structure within it, or a sort of wiring diagram. So there are several switches on the box which can be turned on or off. I think there's 6 here. There's also a set of lights that might or might turn on depending what you do to this box. There's a testing toggle and a coin slot with which you can sort of pay to test this box and try and figure out how it works. And for many subsequent experiments, we fell back on the old online version of this because this turned out to be too stochastic into how it actually behaved. But yeah, the goal is to establish, in general for these experiments, was to establish which switches are working in terms of which switches are connected to the light. You get to keep any coins that you've got left at the end of the experiment if you manage to figure this out. So there's an incentive to do this efficiently. And furthermore, you know that if any of the working switches are in the on position when you put a coin in and switch the toggle, then the light's going to turn on. So one experimental version of this, you've got 6 switches, £6 coins, and you're in one of 2 between subjects conditions. I'm just going to highlight this one here. So the sparse condition, you also get told that only one of these switches is working, giving you sort of an opportunity to further constrain the hypothesis space. So to really spell this out, you've got 6 possible causal wiring diagrams. These are the kind of causal graphs of them. A is the 64 possible ways you could turn switches on and off before you put the coin in and press the toggling switch. D is just whether the light turns on or not. And if you're in this only one of the switches works condition, what do you want to do? Turn 3 on. Right, yes, great. So what would you do? The starting point for this as a sort of developmental study was noting that in science education in the US, kids are basically taught to always test one thing at a time, and that is the way to learn about things in the world. And this was a kind of an attempt to show that that's not necessarily universally true. So the sort of test one at a time strategy is something that would work here, but it seems for smart information gain versed people in the room, that's not the best you can do. If you can do better if you try to narrow the space by splitting the sort of space in half each time by testing multiple switches at once. And yeah, just to really spell this out, the test one hypothesis at a time strategy will allow you to sort of narrow your hypothesis space by ruling one thing out at a time, unless you get it. On average, it's going to take you, like 3, 4, 5 goes. And from an information norm perspective, that's because you don't get very much information per test. You get much less than the maximum one bit of information you can get from a sort of the best possible binary test you could do. Whereas same analysis, but now for the sort of split half or test half the remaining options thing, what you're going to be doing is ruling out multiple things per trial, getting more information in expectation, coming away with more money in sort of on average and in the worst case. Okay, so just one result on this, just to sort of try and capture what we generally find. So this is for different switch boxes with more and more switches on them, and this is with adults. And if you look at the sort of the most extreme case where there's 20 switches on it, you can see that in the sparse condition that I just showed you, for the first trial, around 50% of participants are doing the information efficient thing. They're turning on 10 switches. Another 49% are turning on one switch, or 40%, and then some people are doing something kind of in between. Yeah, go for it.
Clarification question here. So this is kind of depend on the assumptions that people are making.
Oh yes, it definitely does. Yeah. Well, so this is, you need to know you're in the sparse world for this to work. Otherwise,
for
you're.
example,
Yeah.
I might assume that if you say only one switch works, I might assume that turning on more than one switch at a time, they might interfere with each other. There might be some kind of disjunctive or conjunctive rule.
Yeah, so if you're actually working with a more like interactive hypothesis space, then yes, then split half is no longer a good strategy. Well, certainly you could do it, but then the information you'd need to really be careful to keep your hypothesis base straight and the implications straight. But yeah, we'll get there in a bit. Initial summary, at least sort of half of adults, a similar proportion of children, adopt the expected information gain efficient strategy when it makes sense to do so in this task. If they're in the dense condition, which means they know that all but one of the switches work, they fall back on the only strategy that works, which is to test one thing at a time. So we argued at the time that children's failure to control variables may reflect adaptive decision making. It's striking that a significant minority of people still test one thing at a time, which is inefficient, but it is simple and it is reliable. What happens to this relationship with the rational norm as we move towards less constrained settings? And I'm going to try to talk about 4 different projects, or just give a taster of 4 different projects in the next 30 minutes. Starting with a sort of much more difficult case of trying to figure out the causal wiring diagram. So active causal learning in probabilistic causal systems. So here we have a bunch of experiments I did back in my PhD where people are trying to figure out the relationships between 3 or 4 components in a sort of abstract causal system. They know that the system is noisy, so they know that when a cause is active, it's not always going to trigger its effects, but usually will, and that sometimes things will turn on all by themselves, so things are a bit difficult. And they can now perform tests which fix any subset of the components of the system, either to turn them on, turn them off, or leave them free to vary and see what happens. And they're going to get to do this a series of times. So in this case, they're going to get 8 tests to try and figure out how this causal system is connected. And between each test, we're going to ask them again what they think the causal structure of the system is, and they're going to mark it by clicking in between the components and drawing where they think the arrows go. And we're going to be rewarding them based on how accurate those drawings are at random, unmarked time points throughout the experiment. So you better be doing your best with those judgments as you go. I'll show you a video. So here's they've intervened, they've turned on the bottom right component, they've left these 3 free to vary, they've tested it, and these 2 things have activated. They're making an initial guess of what they think might be going on, and now they get another go. And they're going to get to keep going and try and improve. So doing something vaguely sensible, getting some evidence that perhaps challenges the working hypothesis, and they're going to update. Different levels of noisiness between experiments. Some cases they knew how noisy it was, other cases they didn't. There you go. And that's, in terms of kind of causal graph space, we're here. So there's 543 acyclic arrow diagrams connecting 4 variables. Have looked up to 6, at which point there's 3.7 million. So this problem really explodes in hypothesis space, also in your sort of action space, and the less you control your tests, the wider the range of possible outcomes they could have is. So it's generally sort of gets gnarly fast. Nevertheless, participants, are able to arrive at the end of their learning with a causal hypothesis that's actually generally fairly accurate. We show that it's quite closely related to the posterior probability that causal structure that they've marked is correct, given everything they've seen. It's kind of impressive. It's not the sort of hard max, but it's a probability matching type of strategy. And yet, when you look at their structure judgments from trial to trial through the problem, they don't look like that anymore. They're very autocorrelated. So if someone marks a particular causal model at time point 4, it's way too similar to the causal model they marked at time point 3, given the sort of new evidence they've got. They're kind of sticky. They seem to make just 1 or 2 edits relative to their previous judgment on average. So in the paper, I'm not really going there today, but we show and we argue that participants are not really representing the hypothesis space at all. They rather have a kind of current working hypothesis as to how this system works, and they are revising it locally. So they're rethinking particular causal edges or sub-models conditional on what their working hypothesis is about the rest of the model. This implies that they don't have the resources they would need to even do the normative information seeking, even if they wanted to, because they don't have a prior over the 543 models. So there's no way for them to calculate. They don't know how uncertain they should be about things. But we do find that participants perform generally informative types of interventions. Right? So, but they don't seem to perform them in the order that an ideal Bayesian learner would do. So they learn, well, they don't fix everything, which tells you nothing. That's a bad kind of intervention. If you fix all the variables, then there's nothing at stake. They don't fix nothing very much, because that, in this case, is a sort of very uncontrolled and ambiguous test. Either nothing will happen or lots of things will happen, but you won't know what's causing what. They do like to turn on one thing and see what happens. And particularly later during learning, they like to turn on one thing and turn on n-2 of the other things, which you might think of as more of like a controlled test of a specific relationship. And our best fitting model of how people were doing this, we assumed a sort of 2-stage process. We assumed people first selected a manageable local sub-problem within the global learning problem, where we considered these to be kind of potential local foci. So they would either wonder about what's going on between a particular pair of variables, they would wonder what a particular component does, so what all of its direct and indirect effects might be, or they might wonder if their current working hypothesis is exactly correct. And these are all kind of like narrower research questions that you could ask without grappling with the whole global learning problem all at once. But then they would select an intervention that was diagnostic for answering that sub-problem, crucially conditional on what they currently think the rest of the model is doing. I'll give you sort of an example of why that matters in a second. And when you fit this model, step 1 fits very sort of noisily, so that the selection of the next question to ask doesn't seem to target rational uncertainty that strongly. But step 2 fits very tightly in that what the model thinks they are focusing on, they do pick a test that's very diagnostic towards. It's a very old figure. I don't like the color scheme or anything, but it's this is in one of the experiments we also asked them, what are you trying to figure out right now, after they decided what they wanted to test and before they saw what happened. And human research assistants coded their answer as what it referred to, whether that was a particular, we also displayed labels on the components for this version of the task. So they would be like, I wonder whether X causes Y, or I wonder what X does. And then if you compare that to what our modeling thinks is the local focus that is best resolved by the test that they did, there's a good overlap here. So very often what they're doing makes sense for what they say they're wondering about. And kind of interestingly, there's some shift from, when you know nothing about the system, people quite like to, they say they're wondering what a particular component does, which often correlates with just turning one thing on. Kind of halfway through, they often say that they're wondering about a particular edge within the model. And on the final trial, they, to some extent, say that they're trying to confirm their hypothesis. So this all sort of seems relatively intuitive. So, you know, based on this oldest project I'm talking about, we figured that locally focused testing strategy is kind of synergistic with a locally focused updating capability. So if you recognize that you can only really, you know, locally target and update your model, then it makes sense to sort of account for that in how you even try to gather information and try and gather information, you know, that's relevant to a subproblem. It means you only need to engage with a few conditional probabilities at a time without ever trying to sort of deal with the whole space of unconditional probabilities. And you can also kind of learn to actively learn. So you do this over and over again within this task, but arguably also within life. You're often trying to solve these kind of narrow problems, so you can figure out what's a bad and a good way to do that without having to, in the moment, posterior calculate the possible outcomes of everything. This is just an illustration of if I care about whether this causes that, and I think this is my kind of global model, our modeling framework would say the test that you're going to perform is one where you're going to have to turn this on, but you're going to need to control this one by turning it off, because otherwise you're going to get a kind of confounding data from that. But because you haven't considered whether this is part of the model, you're going to ignore this, and potentially that might lead you astray. Okay, so that was active causal learning in probabilistic causal systems. The hypothesis space was kind of large and compounding, but at least you had independent tests. You could at least perform interventions on independent trials and be sure that each trial was totally separate from the next one. In this line of work, that's no longer the case. So now you're still trying to figure out the structure of causal systems, but you're doing so in time, which means that the components that are connected in these systems are probabilistically triggering one another, but also with sort of variable delays. So this causal model here, you see there's a bidirectional relationship between A and B causes C. This means that, you know, one potential timeline of someone engaging with trying to figure this out, they might intervene and trigger A, which would then start a cascade of A, B, while also repeatedly triggering C. In a way that you could imagine, if you didn't see the dotted lines, would lead to quite confusing data. After a while, something fails, the system sort of calms down, they perform another intervention, and again. So now the sort of action choice question has another dimension to it. It's not just what should I do, but when should I do it? Hypothesis space large. We did 3 and 4 variable problems. Now you have cycles. There's even more possible causal models. And your action space, in a sense, is a bit smaller because you're not doing these controlled tests, but in a sense, it's much larger because you get a minute or something, and every instant you're deciding, should I do A, B, C, or wait? And no longer can you lay out the possible things that could happen exhaustively, because that's, you know, there's an infinite set of possible precise timings of things. But if you want to be kind of approximately normative, you can still sample things that might happen in order to make sort of decisions about whether to act or not. And the horizon suddenly is long because you need to worry about stuff that you did earlier still happening, still potentially not having resolved, and there's a sort of general online mess going on. But, you know, can people information seek in this setting in a way that's sort of systematic and sensible? This is just a kind of layout. I've kind of already said this, but this is what the experiments look like. You had a budget of interventions. In some conditions, you could also perform controlled tests, so you could turn off components and leave them turned off until you turn them back on again. But you're activating interventions are like triggers. You click on something, it happens, and then you wait and see what happens. And as before, we're trying to incentivize information seeking efficiency because you're being paid based on how accurate the causal edges you've drawn are at random time points during these tasks. So you need to try and make progress and tell us what you think as quickly as possible. Here's an easy one. So, started? Yeah. So try and sort of think through this. So, Seems reasonable. Uh-oh. So now that happened, but that didn't happen, so there must be something wrong. And then they've already got this one right. So this is about as easy as it gets, with the space of a couple of interventions and a bit of reasonable sort of waiting for things to stop. They get structure right. But because I'm kind of a cruel experimenter, we also had problems that look more like this, where there's cycles, things going on. You create too much, and it becomes very confusing to you. So I need to keep moving. So the sort of high-level result that I'm going to try and convey here, while skipping over all the details, is that participants were generally able to solve these tasks, at least as well as the contingency-based ones. You see the human accuracy in green here. And successful participants, necessarily were ones that with their interventions, produced the information they needed for an ideal observer to get the answer right. So they needed to produce informative dynamics, but they're also in this kind of top left corner of this plot, in that they tended to be the ones that didn't also produce too much dynamics. They produced sort of minimal but informative causal dynamics from these systems. They didn't trigger really dense cascades of evidence, or if they did, they would control them and stop them again. So we modeled this by sort of refining what we thought the sort of norm should be here, that rather than just trying to generate as much information about the causal system as possible, you should be doing this with sensitivity to your own learning limitations. So we took this sort of resource-rational cognition framework, and we said that actually, human minds need to trade off between the costs and rewards of computation, and in this case, there is a real trade-off, because when you produce dense event dynamics, our sort of normative learner can still consider all the different ways that the variables could be connected under all the different hypotheses, but there's just a much larger set of these that need to be kind of grappled with. So in reality, the amount of time it took our model to fit the data for different trials was, super dependent on how much stuff was going on in those trials. So yeah, rather than framing the utility of people's sort of action choice as just expected information gain driven, we're modeling it as expected information gain minus expected computational cost, where computational cost is a function of the kind of momentary event density that you're expecting or anticipating to be coming down the road at you. And just to give a sort of taste of how this model works, let's look at just a little fragment of one trial within one of these tasks. So here we've had, the participant has intervened on A, second later B's happened, they've waited a little bit, they've intervened on C, waited a little bit, intervened on B, C's happened. If you just model the expected information gain as a rolling function of where they are right now with the prior and everything, you can say, how valuable would it be at every instant to either do A, B, C, or wait? And the information gain maximizer is greedy, so it's always, the colored lines are always above the gray line. It's always saying, do something else, add another intervention in the mix. Let's get more information, let's get it now, let's get more money. So, practically always favors acting over waiting or blocking. Whereas if all you cared about was not, I don't want stuff to happen, I don't want to have to do computational work, then obviously you're always going to favor doing nothing. And how much you care about that is going to depend on how much you've done recently, so how much you're kind of expecting to still be going on, because these costs compound with the sort of density of the events. So here it's saying, once you've done A, let's wait a bit. Let's definitely, it's going to be costly to do something else. But that cost diminishes once things calm down. When you put these things together, you get a model that can sort of assign a more likelihood to what the participant actually did, which is mostly wait, but once things calm down, do things that they hadn't tried yet and they haven't seen yet. So, at this point, you've done A, you've seen B, nothing's happened for a while, it starts to be worth doing C. So, this framework, unsurprisingly, beat the expected information gain maximizing framework in capturing participants' learning and their intervention selection. And the version of it that worked best assumed a sort of short horizon over which you care into the future. You're not thinking about the whole rest of the trial, but the density in the nearer future. So we kind of concluded that people time and target their interventions to produce simple yet informative dynamics, which challenges the sort of the norm. And off the back of that, I've been involved in a collaboration with some people at MIT. It's not published yet, but it's in R&R, so fingers crossed, where we sort of try and distill this argument, and we apply it to another information-seeking game called Mastermind. Who here has ever played or knows what Mastermind is? Half or less. Okay, cool. It's a code-breaking game. You're trying to figure out the hidden code by trying codes. It's like you're trying to figure out, like a combination lock. So the code is some, series of numbers 1, 2, 3, or 4 in some order. But you get this kind of annoying kind of feedback. You get told each time you try a code how many of the slots are exactly correct, and how many additional how many additional numbers have you put in the code that are correct but in the wrong place. That's this misplaced second column here. And the reason we studied this is if you look at all the play data of this game, people are systematically anti-correlated with information game. So if you look at what people do, and then you line up all the things they could do according to how information efficient they are, most actions are down in like the 25th percentile. They're way below chance. If they did random codes, they would get more information from an information game maximizing perspective by a long way. But we explained this by assuming people have a limited capacity to actually process this information, and we modeled this as a sort of trying to represent the likelihood function implications of that data with respect to the problem. And the way our model works is it has a sort of working memory bound, so it can only represent things, constraints that it can mentally describe in a fairly simple way. So a test like this, 1, 1, 1, 1, 1, and feedback that exactly one thing is correct, is simple because it tells you something simple. It tells you that there's 1, 1 in the code. And doing this tells you there's 1, 2 in the code. So still you have kind of information you can represent. But doing something like this gets you really confusing information because you learn something like, I know that there's a 1 in position 2 if there isn't a 3 in position 4, so long as there isn't a 1 in position 1, and that kind of thing. So you get the completely difficult to represent information. And if we assume people kind of overwhelm their working memory with this and end up having to approximate it with something that's not quite right, then you get a different information gain norm, and suddenly you get a sort of a bounded information seeking model under which participants' interventions are almost optimal if you pick the right bound. It also explains why if you give them high information codes, they can't solve the problem. If you give them low information codes, they can if you give them the right ones. So it's pretty convincing. And the way I like to tell the story is it's like you have to go from the low representational complexity state of knowing nothing to the low representational complexity state of knowing everything without ever going through any really high representational complexity states. So it's like you've got this kind of limit and you've got to take lots of little steps to get there without overwhelming yourself. I talked about Mastermind because I think it's more colorful, but actually we also did it with essentially the switchbox task on hard mode, so the thing from the beginning. Now there's multiple switches work, and you get the feedback about how many of the on switches are correct. And we find the exact same thing. People are anti-correlated with the information-seeking norm. Right. I do want to talk about this one because it's fun, but I'll try and make it quick. What if you don't just have continuous time, you also have continuous space? So this is a project where we were interested in how people do information seeking in physics-simulated microworlds, where we ask them about properties of these objects in the world, and then we allow them to do continuous control of the objects by using touchscreen or mouse control to grab these objects and move them around. Think of this like an air hockey table from above, and you're able to essentially like reach onto the air hockey table and move the objects around. If you don't do anything, you'll just see them bouncing around, but you can curate those dynamics by performing actions. And we gave people one or both of two inquiry goals. They were either trying to figure out whether the two labeled objects, which one was heavier, or they were trying to figure out if there was a sort of force-like relationship between them, if they attracted or repelled each other or didn't affect one And we were interested in whether they could answer these questions and also what they would do depending on the question. What you'll see I'm going to show you a video in a second, so you're going to try and figure out the answers to these questions yourself. Bear in mind that the sort of cross symbol is where the participant's finger or cursor is, and the thick black border is the object they're controlling. If they have grabbed an object, it will get a thicker border. I might need to play it more than once. So ask yourself if you can tell whether these objects attract or repel or don't affect one another, and if you can tell which one is heavier. And if you've got any bandwidth left, try and think about whether what the person's doing is a sensible way to figure that out. Anyone want to hazard some guesses as to the answers? I'm going to start it over. Now you've orientated a little bit. So there is no force relationship between these objects. What about the mass? Age is heavier. Age is heavier. Yeah, it's pretty unfair to throw you in without any pre-training. But we have the physics simulator, so I can still do normative analyses here. I can play forward the physics, the actual physics, and all the counterfactual dynamics you would get under all the different hypotheses about not just these kind of target properties, but also the other things I didn't tell you, like what the force relationships are between the other objects and so on. So we can measure information from a sort of normative perspective, but we can also try and characterize what people are doing and how sort of adaptive it is. Continuous action and data space. There's a large nominal hypothesis space because we sort of randomly sampled the force relationships between the distractor objects and the target object, although you were actually only trying to answer this narrower questions. And people are adaptive. So if you do this analysis and you give a sort of arbitrary level of perceptual precision to it, you see that mass uncertainty is lower for participants who are trying to figure out the masses of the objects than for participants who are trying to figure out the force relationship. Force uncertainty is lower for participants that are trying to figure out the force relationship than and this is all within subject, so the same participant in the same world will produce information that is selective. And we also got human coders to watch all the videos of people's interactions with these tasks, and for every action they took, categorize them into a set of different kind of qualitative test types, which were things like launching, which was like grabbing a target and throwing it at another target, knocking, grabbing a target, tapping it against another one without letting go of it, throwing, grabbing a target, throwing it at the wall, essentially. And we can measure the sort of information profiles of these tests over the sort of period after during and after the test. So this is, if I take all the things categorized as launching and I align their onset time and I measure how much they fork the predictions of what's going to happen next, depending on the ground truth of the two questions, then you get these kind of informational profiles. So launching produces a spike in mass information, around when the object hits the other object, when the collision occurs. Throwing, you get mass information as you kind of accelerate the object, as you fling it. Shaking produces lots of mass information for a longer amount of time, more unmistakably. Participants that discovered and used shaking tended to get the mass question correct, for example. What we called encroaching, which is like moving the objects close together, holding them close together, was the sort of a great way to discover the force relationship. And there were also things that were more about removing nuisance variables from the equation. So this would essentially reduce the baseline divergence, so the divergence that didn't depend on the target properties but on the nuisance properties. So blind to condition coding of these categories, and then you reveal which condition the participant was in. It's quite dramatic that participants who are trying to figure out the mass do a lot of smashing, bashing, and crashing, while participants who are trying to figure out the force relationship, they do the dominant behavior is this encroaching thing. Kids can do this just as well as adults. So 4 to 10-year-olds were formally as information efficient and adaptive to the inquiry goal as adults, which was surprising because they were then not as accurate at telling us what the answer was. But I think that's a kind of independently interesting finding. But yeah, so this is a very high-dimensional active inquiry setting, and yet it's kind of impressive how systematic and goal-relevant participants' actions are. They're creative, compositional, and systematic. People do these kind of multi-step actions that involve moving around the space at sort of in systematic ways. But they're not doing what our information gain maximizing model does, which is basically scrub the objects around at 100 miles an hour and create information that only it could use. They're more trying to sort of isolate, control, and exaggerate properties, which I think is relevant to the talk. And also relevant to the talk, and the title of the talk is that these tests only even make sense conditional on you, the watcher, the participant, all of us understanding physics already. So they're about like exploiting physics to reveal physical properties. They're not if I took as I have sort of tried to do, a learner that doesn't even know what physics is and try and learn physics from, then it would have to do very different things, and it wouldn't look anything like this. So these are still kind of narrow tests conditional on physics. And they reoccur. If we believe this task is at all realistic, then these are things that you've been doing since you were a baby. You're trying to figure out, how heavy is this? Like, how tactile is it? You have these kind of basic inquiry goals that reoccur, and you can learn how to do them through trial and error. What if we make it even harder? So we've gone towards continuous data space, continuous action space, large hypothesis space. What if the hypothesis space is unbounded? What if it's kind of essentially infinite? What if we kind of try and think of a situation that's maybe more like you are in as a scientist trying to figure out how the world works, where there's kind of no limit to the number of theories you could put on the table. So I've had quite a lot of fun using this game called Zendo, adapting it into an experimental interface. This is kind of like a tabletop scientific induction game for nerds. Somebody plays God and decides a hidden rule, and then everyone else tries to figure out that rule by performing like mini experiments. And the world we use is a kind of alien planet with objects which are kind of little triangular cone things. They saliently seem to have a size feature, color feature. They also have kind of arrangements. You can put them in any kind of way. They can touch, they can lean on each other, and so on. I'm not very specific about what does and doesn't matter. And to motivate this scenario, imagine these two scenes produce a strange new form of alien radiation. These two don't. Audience participation. Has anyone got any hypotheses about what might be determining what makes a scene give off radiation?
A small little cone tipped on that side.
I like that. So a small cone on its side. Any other guesses?
Small red.
Small red cone. On its side. And on its side. Great. Yeah. So small red cone, small cone, cone pointing left, cone on its side. Red closer to the bottom left. The longer I make people do this, the longer the list of hypotheses gets. Some of them seem better than others in that they're simpler, but with 4 data points, most of them are going to be able to be like at least consistent with the data. So spend a lot of time thinking about this because this is a case where just to even explain what you all just did seems to imply that our ability to generate hypotheses has this kind of compositional language-like productivity. You can just keep generating them. And getting a good one seems to be a process of generating, but also adapting them in the light of like ever more data. But for this talk, the question is, what if you could produce a 5th data point? What do you want to do? Like, what would you want to do? And actually, all the data I've collected on this has that structure, because what we did is we gave people a single positive example of a concept. So we drew one scene for them. We said press test, and it would give off psi waves, And then they would get this construction interface, and they would just be told, you've got 7 more goes. You can perform 7 of your own experiments now. Each time when you're ready, click test, see whether it follows the rule. After you've done 8 tests, you're going to have to make some generalizations to a set of scenes that I've selected, of which secretly half of them follow the hidden rule. And then you're going to give me a completely free text guess as what you think the rule is. We've done this with children and with adults. For a variety of hidden ground truths. Almost doesn't matter what the ground truth is. These are just things that came out of my mind. But they're kind of, they're single features, combinations of features, quantifiers, kind of different possible combinations of what could be going on. Now, people are able to make progress in this, so they're able to generalize somewhat above chance, both children and adults, after 8 tests. Not miles above chance, but 60-70% of the generalization case is correct, and there's sort of somewhere between like a 0 and 40% chance, depending on the problem, of them getting exactly what I wanted them to learn. But when they don't, they generally, about 75% of the time, still say something that fits the data that they have generated, just perhaps something too complicated, and often fits the generalizations they made as well. And I think, again, for the purposes of this talk, it's striking that trying to model this as information gain maximization provides very little traction. I have generated 1 million hypotheses from a prior over all Boolean functions, and then 1 million test scenes, and then selected the test scene out of that set that best forks that best reduces uncertainty across my prior sample, and it doesn't do any better than participants, adult participants. So that's the dark grey line is uncertainty-driven testing. Green line is what adults did. Black line is random tests. They're all kind of pretty similar. Kids systematically a bit less than random, but as we've already seen, that's not necessarily doesn't mean that they're not doing something that's sensible for them. Very briefly, the empirical signature we see here is one of, again, autocorrelation among the tests. So for adults, seem to produce scenes that stay quite close to the positive test we gave them in terms of the feature distance. If I were to edit their scene to turn it back into the initial test, you can see this kind of like dark shadow along the top. That's a kind of anchoring on the initial scene we gave them. And there's also this kind of dark shadow down the diagonal that the thing they do next often resembles the thing they just did before. And characteristically, it's things like do what I just did but remove a cone, or do what I just did but change the color of all the cones, or add a cone, and so on. So I think in this fully open space, it seems like expected information gain is no longer a very useful way of thinking. Local search in both the hypothesis space and the data space almost seems like it's the only game in town, because you've got to come up with your next test from somewhere. You've got to come up with your next hypothesis from somewhere, and where else but what's already occurred to you. The kind of global hypothesis space is dominated by the sort of unknown in the Donald Rumsfeld sense, the things that the person who's learning has never even thought about yet. This problem becomes much easier if I give you a set of hypotheses, including my hidden one. This becomes a much, much easier kind of task. So it's really about generating that right hypothesis. But it seems like controlled experiments in this kind of setting are safer ways to test minimally different possibilities, given that the more you change, the more that's going to sort of interact with all of the hypotheses that you don't even have in your mind. So this took me to a phrase that Yoshi taught me about in my trip here, the theory of the adjacent possible, which comes from Stuart Kauffman in this nice 1996 TED Talk. This is an observation about the nature of human innovation over time as a sort of connection to biological evolution. And while biological systems evolve through small steps, similarly it seems to go with the way theories change in our society. That we at any one time in history we seem to be quite limited to a sort of narrow horizon of conceivable next possibilities, which are kind of determined by the technology and concepts of the day. But when someone does make a sort of useful forward step, then that kind of unlocks a whole new space, a whole new adjacent possible, and then you get these weird dynamics where people suddenly make a lot of progress and then get stuck for a long time because of this narrowness of the search process. So, and it implies that when I'm testing hypotheses in the Zendo task and someone else is, we're probably quite far apart in the global space relative to the sort of horizon of things that are occurring to us. So it's quite a different picture of active learning. So I think this sort of suggests that a better way to think of the goal of information seeking as being something like maximising your mobility within your personal adjacent possible, by which I mean, taking actions that produce information that at least have a chance of allowing you to take a step in a direction from where you are right now, and if you're going to take that step, trying to maximise the probability of it being a good step. And that way you never really think about the global problem or whether your background assumptions are all correct, but you at least make kind of positive progress and don't induce errors that are hard to fix. I think this kind of means that when you take the normative perspective, what you see is what looks like confirmation bias, because everyone is working in a narrow space and you're looking from a sort of unrealistic global space. So it just seems like they're just staying very close to what they believe right now, but I think that's just an inevitable fact of life. Perhaps I've rediscovered the starting point of this, that control of variables isn't so bad after all. Take-home messages, because I'm out of time. Outside these constrained tasks, information seeking diverges, I would say, diametrically from expected information gain maximization, because the consideration of the whole space is usually infeasible, let alone the whole pre-posterior space of possible futures. The globally informative evidence increasingly becomes impenetrable or uninformative from the point of view of a realistic learner trying to sort of teach themselves something or improve their beliefs. So strong localized evidence of the sort you get by controlled tests seems to be more reliable fuel for metaphysical mobility within the adjacent possible. Fortunately, these objectives become kind of repetitive. You keep taking little steps. They keep being like, does X cause Y? What does X do? So you can kind of learn strategies for solving these questions and then generalize them across lots of reoccurrences. And with 3 minutes for questions, I'll end there. Andy.
This was very cool. I found myself wondering, it seems like all of your examples are examples where assuming that the actual thing to be learned is not super, super complicated, this is actually a decent strategy given our information. But imagine if the actual thing was like this incredibly recursive tangle of conditional loops or whatever. My intuition is that this approach would actually not lead you anywhere, right?
Well, there is a sort of worse.
Yeah.
Oh, sorry. Yeah.
Sorry. So that's part of it, and then the
Yeah.
other part is, but it might. Is there a way that you could see it might not lead any individual anywhere, but if lots of individuals are in different places in the space, it might still lead somewhere. Yeah.
Yeah. That's definitely part of the thought is that lots of narrowly focused individuals are like particles, making kind of little local moves in the space, and you need lots of individuals to have any coverage of the space, and then you have all these opportunities for social learning where you can jump ship and swap to someone else's adjacent possible because you can see that it's miles better than yours. But I think the first part of the question, like the worst possible case is there's no traction, right? So the worst kind of the switch version of the switch box is that there's an interactive function involving all the switches of any possible function, in which case the only way to learn that function is to try every single combination of switches and just write down what happens for that combination, and there's no generalization possible. So a hidden premise here is that we're somewhere between the no free lunch worst possible world and the super simple best possible world where you can boldly perform uncontrolled tests and assume nothing is interacting.
And that's why universities are such great social structures, as curiosity-driven as opposed to strategy or bureaucracy-driven. Yeah, that's why they've served us so well.
Yeah. Because a big problem here is like learning traps. Like active learners don't have amazing idea of where they should go next. So there's a lot of opportunity for of teaching other people your insights and piggybacking off each other. I think things get a lot better then.
Maybe this is a half-baked thought, but do you think the reason that humans kind of use this local optimization strategy cropped up so much is because it works in the real world, like because there are more correlations in the real world and more statistical redundancies between different states, then we might test and say these kind of experiments or even like constrained games like mastermind or that kind of
you think local testing works because the world
Because the
world is modular, or something?
information, yeah.
Yeah, I think that's an interesting hypothesis. Hard to test, but plausible hypothesis. I tend to couch it in Gibbs sampling. I have this thought that like my global model's probably wrong, but I can't even consider wholesale alternatives to it. But what I can do is I can like assume 99% of it and relitigate 1% of it. And so long as I do that in a balanced way, picking different 1% to relitigate, then I'm making moves that have a kind of positive average in concept space. So I'm going to find my way to better theories, and then depart from those theories again, and then find my way to another good theory. But at least I'm mobile, and at least I'm kind of evidence sensitive. That's the way I kind of think about it when I'm trying to be as global as possible.
Yeah, one idea that like kind of popped into my head as you were talking about this, kind of local testing and that thing, explaining what humans do. Have you thought about at all about how this like connects to philosophical theories of truth? And like in particular, it really reminded me of the pragmatist conception of truth that William James and the like talk about a lot, where they define what are useful scientific theories or true ideas as not being like this abstract, like, you know, forced from context thing, but it's a very humanly useful thing. Like true ideas are those ideas that can be like assimilated, validated, corroborated, verified. So in other words, like true ideas are ones that are like kind of more incremental in a way, and that can connect to your like direct experience.
Yeah, I mean that sounds sensible. I think I'm quite Quinean, so I'm very coherentist about truth. And as a training in Bayesian, I think the truth is a random variable, so it's also just something we can kind of aim at, but you can never really claim to have.
Right.
But then pragmatically, I think truth gets used in other ways than that. That there are things that we're happy enough with, given the sort of shared context that we're going to call them common ground or true, or something like that. But yeah, I tend to reserve true for something that you're never going to know.
I was just wondering if you've tried giving people like more cost to being kind of wrong in a way, because one thing I was trying to think about is when you're trying different versions of like testing out the world, and there's a cost to you being really wrong, I guess you're less likely to test, so you're more likely to be locally optimal or kind of unwilling to change stuff. Like I was thinking of an example of like when I swim in a swim team, one of the things is they'll tell you like you should swim butterfly incorrectly with this arm and just see what it feels like, and then try this new way of doing it. And then you'll be like, well, if I'm in a race against a whole bunch of people, I'm not going to try that during the race and be like, oh, it'd be a fun time to test that out. But you kind of want to balance those competing objectives. You want to do enough just to test and learn, but not too much.
Well, yeah, you're trying to learn while already using your model and having all sorts of goals already. And the common thing across all these experiments is that we try to make the utility pure information, which I know is unnatural because it's always mixed with an exploit problem in life. But in these cases, you are there's a proper scoring rule in the sense that we want, the amount of money you'll walk away with is a function of how efficiently you can arrive at accurate beliefs about the task. So that's an attempt to sort of isolate information seeking from its utilities. I would note that even when you add utilities, if people are in an information seeking mode, they're pretty insensitive to them. Todd Garekis has shown that. You can pay people very like unbalanced ways for like sinking ships or something in Battleship, and they still sort of tend to have this kind of, once they're in inquiry goal mode, then it's hard to also add the utilities on top of that. I have information from the causal learning task, actually, that we have an information-seeking version and a utility maximizing version, because in the very earliest versions of those experiments, you got paid different amounts for like getting positive arrows versus omitting arrows that you should have had. And people, the modeling suggests that people aren't thinking about that when they're choosing their tests.
Time horizon.
I just had the thought that initially that comes out of this really nicely. Almost what Philip's point was about universities is that it's true that we're under resource constraints as learners, but one of the other great advantages we have is that we're social creatures, and that we can set people off in different initial conditions. And so like the next step is then to see, well, do people use efficient strategies when we can kind of let multiple chains run from different initial conditions and then come together and trade information.
Yeah, it changes the character of the problem again, because you can be a crank who pursues a really low probability thing because you know that there's someone else will do the other ones, and maybe you'll be right and you're the only person inhabiting that part of the space, so you could become very successful and stuff. Yeah, so I think there's some repulsion effects in some of these spaces where people try and do something different from what other people are doing. So it's because at least then they're not going to have to share the rewards if they're right. But yeah, I'm aware I'm over time, so people should feel free.
I think we're 5 minutes over, so this is lovely, but let's talk to me.